You can get results from this where you can't get results from lasers. Lasers get bleached out in sunlight. I had a colleague that I was speaking to who went to Mexico to do crop scanning, and he had a handheld laser scanner, and he had to do it at night in a tent because the sun wrecked the laser scanner, and there were wolves about, and it was a big problem for him. If you'd have just used a camera, you might have found that you've got to work harder on your stereo matching, but there are things it will do that laser scanners can't. So there's going to be a time for one and a time for the other.
The top tip for the day is use a stereo pair of cameras, don't get eaten by wolves.
Yeah, that would be my advice. We find corresponding points in our left and right eyes, and then we can use that to work out how far away from us something is. When we have an individual eye on its own, we have some monocular cues, some monocular clues, as it were, that we can use to find out depth, or at least to estimate depth. But true 3D only comes from two eyes. In a single eye, you might have something like the object is bigger than it was before, so it's coming towards us. Or one object is passing our view faster than another, and that parallax, and that gives us a clue that it's in front of something else. Occlusion is an obvious one. If something actually is in front of something else, we can make some reasoning about that. So our brains will take those monocular cues, and do something with them and work out what's going on. But when we have two eyes, then we can do actual 3D depth perception. The classic example is those magic eye things that were around in the 90s. I'm not very good at seeing those. I kind of cross-eyed and it kind of works, but it's all a bit backwards. But the idea there is that we trick our eyes into seeing slightly different images, and that gives us a perception of depth. If we've got a stereo system, the main thing we need to know is where are our cameras. Our brains know where our eyes are because they've learned it, but one's here and one's here. You know, people maybe have slightly further apart eyes. But your brain will account for this. If we're going to do this mathematically using a computer, we need to know where these cameras are. If you know that we've seen an object in one view, and then we go into the other view, we need to try and find corresponding points. Without knowing where the cameras were, your search space is increased. You've got to look over the whole image. Maybe you get points confused. Maybe there's a corner that appears multiple times because it's like a book and it has 4 corners. And then you've got to try and resolve which one's which. And some of these features won't appear in both views because of occlusion. So if you take your left and right view of my hands, you know, some of my left hand is going to be visible from one eye, but it isn't in the other eye, and that's a huge problem. So what we do is we start with a process called camera calibration. We have 2 cameras that are nearly next to each other, and we don't know exactly what their angles are, but we can find that out by using camera calibration. We have to take the picture from both cameras at the exact same time, because otherwise the scene's going to have changed. So we'll assume we're taking pictures with the cameras at the same time, something that isn't true of some visual reconstruction systems. We take a picture of this board, and we calibrate the positions of our cameras, and then we move the cameras and take a picture of something we're trying to reconstruct in 3D. So then we have a situation where we have one image here on this side, our left view, and we have an image here which is our right view. In our previous video on Matrix, we talked about the lens and all this system in front. We will do away with that for now, just for simplicity's sake. And we'll say that these are pinhole cameras. Because we're using a pinhole camera model, the optical center of our camera is somewhere behind this camera plane. So some object in the world projects its light down here, intersects our image plane, and then goes into the camera origin like this. We have our optical center of our camera, and any light rays coming from this object here are going to travel down this ray, intersect our image plane, and then go into the optical center of the camera. And this will happen for any points in our scene that this camera can see. We want to say, we've got a point on this image plane, where did it come from? And the crucial problem is that it could have come from here, or it could have come from here, or here, or here, or anywhere along this ray. And we don't know. And that's what we're trying to find out. That's the depth problem. Now, we also have an optical center for this camera, which is here, and rays will be coming out and intersecting through these points. So if we knew that this point in this image was this point in this image, then we just project the rays, we find where they intersect, and we use simple triangulation, simple maths to work out how far away that position is. We don't know what point that is, because it's going to change. It might not be visible in this image, it's one problem. The search space is quite large. Reliably finding the exact same point as this in a different image when it might have rotated and changed slightly is a lot of work in 2 dimensions. And you've got to do that for every single pixel in this image. You've got to find maybe one that tries to match in here. That's a lot of work to do, so we don't tend to do that. We use a nice observation called Epipolar Geometry to try and make this a little bit easier. If this is our intersection point, x1, and this is some object x all the way out there, and we're trying to find out how far away it is, we need to try and make our search in this image a little bit easier. So what we do is we imagine that this is part of a big triangle coming out. So this is one corner of our triangle, this is another, or it could be this. This X is somewhere along here and comes in through this point. So let me get a different pen, that'll make things easier. We can draw a ray that goes from this optical centre to here, and from this optical centre to here, and from this optical centre to here, to any of these points. And they intersect this image like this. And what this is our epipolar line. So this line here, through these points, is all the possible projections of this ray into this image. So now we've simplified our problem. Because we know where these cameras are, we can say, we're trying to find this position x1 in this image. By knowing that it's going to be somewhere along here, we know it's going to be in this line here. So we've got a limited set of pixels we have to now look through. So all we need to do is go through each of these pixels in a list and say, which one of them looks most like this? And then we find it, and then we find our triangulation point, and we find out how far it is away.
Is this because you already know where the cameras are?
Yes, it's only possible because we know where the cameras are. If we don't, then we have to just search through the whole of the other image, and it takes ages. One edge of our triangle is between the optical centres of the cameras. One is through this point and out into the world, and the other is some value we don't know, which is going to be along this line, because it's just a flat triangle cutting through this image, which makes it a lot easier to find out where these things are. What we will do, if we're writing a stereo reconstruction algorithm, is for every point in this image, and maybe we'll do it backwards as well for completeness, for every point in this image, we will try and find the point along its particular epipolar line that best matches it. And then, of course, you can go much more complicated than that. You can try and find the global image map between here and here, which is a combination of not only the best feature matches, but also, it needs to be nice and smooth. Objects don't tend to go back and forth a lot, so you want them to be rounded, so you have to bear that in mind. Finding a point in this image based on another one from this image is called the correspondence problem. And that's really the core of what we're solving here. Finding the occluded pixels is hard, and there are approaches based on this, where they not only try and find what we call the disparity map, the difference between this X and this X,